Hi, I'm Nithin Varma, a postdoctoral researcher at the University of Haifa. Today, I will talk about our paper Query Complexity Lower Bounds for Local List Decoding and Hardcode Predicates. And this is joint work with Noga Ron-Zewi and Ronen Shaltiel. Here is an outline of the talk. I will first define the notions of list decoding and local list decoding. I will then give an overview of our main results and the applications of our results to black box proofs for hardcore predicates. I will then move on to give a high-level idea of our lower bound argument, which is based on a famous coin problem. I will conclude the talk with some open problems. A binary code ENC that maps bit strings of length k to bit strings of length n is half minus epsilon comma L list decodable if for every word W, which is a bit string of length n, there are at most L messages M, such that the Hamming distance between W and the encoding of M is at most half minus epsilon times N. In other words, there are at most L code words such that W can be obtained from the code word by flipping at most half minus epsilon fraction of the bits. We will refer to this quantity half minus epsilon as the fraction of errors. Now, a locally list decodable code is a list decodable code with the additional feature that there exists an algorithm which we call the decoder such that for every word W and every message M such that the distance between W and the encoding of M is at most half minus epsilon times N, with probability at least 2/3 over the random coins of the decoder, there exists an advice J such that the decoder given oracle access to W and inputs I, J outputs the ith bit of the message with probability at least 2/3. Here the advice J can be thought of as the index to the list element corresponding to encoding of the message M. The number of queries made by the decoder to the word W is called the query complexity of the decoder. We study local list decodability of codes with high encoding lengths, or rather very low rate. A candidate example is the Hadamard code. For those of you are not familiar, the Hadamard code maps bit strings of length k to those of length 2 to the k. The bit position indexed by the string r in 0, 1 to the k is the dot product mode 2, the message m and the string r. Hadamard code has an efficient local list decoder as shown by the seminal result of Goldreich and Levin. For fraction of errors of half minus epsilon, they achieve list size and query complexity quadratic in 1 over epsilon, which is really small. The question we ask is whether the query complexity bound can be improved. Supposing we allow for large list sizes, say of the order of 2 to the big O of k. We ask this question for arbitrarily low rate codes and not just for Hadamard. The motivation for considering such a question comes from the use of Goldreich-Levin theorem to obtain hardcore predicates from one-way functions that are hard to invert. And an improvement in query complexity of Hadamard local list decoding could mean an improvement in these type of results. In our work, we give lower bounds on the query complexity of local list decoding low rate codes. When the value of epsilon is large, say 1 over poly k, we show that the query complexity is omega 1 over epsilon square. This is a tight lower bound, as evidenced by the matching upper bound of the Goldreich-Levin theorem. Additionally, our lower bound rules out the possibility that allowing for large lists might improve the query complexity. Our work extends the work of Greenberg, Shaltiel, and Viola, who proved the same bound for binary codes of higher rate. In particular, the result of Greenberg et al. Does not cover the case of Hadamard. When epsilon is smaller than 1 over poly k, we prove the slightly weaker bound of 1 over square root epsilon, and these two results together rule out the question of whether the query complexity can be 1 over epsilon to the whole power of lit low of 1, even for low rate codes and even if we allow huge list sizes. One of the consequences of our result is in an application of the Goldreich-Levin theorem for obtaining hardcore predicates. The Goldreich-Levin theorem can be restated as follows in this setting. Assume that f is a hard function such that for circuits of size s, they cannot invert f with probability more than rho. For the purpose of the talk, maybe we can assume that f is a permutation. Now, based on f, let us define another one-way function f nu that concatenates the output of f on the first argument with that of the second argument. So f nu takes two arguments. We also define a predicate f pred that also takes two arguments x and r and outputs the rth bit of the Hadamard encoding of x. Goldreich-Levin theorem implies that given as input the evaluation of f nu on an input, it is impossible for circuits of size at most roughly s prime is equal to s over q to compute the value of f pred, which is really a single bit, with advantage of more than epsilon over random guessing. For concreteness, assume that the function f is hard to invert for circuits of size poly k. And again, assume that the probability that the circuit C is successful in inverting with probability at 1 over poly k. Rho is 1 over poly k. Then Goldreich-Levin theorem guarantees that the predicate f pred cannot be predicted with an advantage of more than 1 over poly k over random guessing. Now, suppose we start from a function f that has a much smaller probability of successfully being inverted. That is, f is a much harder function. Do we get any improvement on this epsilon? This is a question that can be asked. No. As we begin with a circuit of size s is equal to poly k, we really cannot get epsilon less than 1 over s, which is equal to 1 over poly k. And even if you do not follow the computation, the gist is that LLDCs with query complexity q is equal to 1 over epsilon to the theta of 1 do not help us to obtain a hardcore predicate for rho even as small as 2 to the minus square root k, and there is no advantage over a rho with 1 over poly k. One can ask whether it is possible to obtain a better epsilon by replacing the Hadamard with another list decodable code. And the answer again is no, because by our theorem for smaller epsilon, this is impossible, even if we use codes with low rate and large lists. But maybe we could do it via some other black box technique instead of this local list decoding technique. Again, the answer is no, And we show that this is impossible for a general definition of black box techniques. The details are in our paper. The proof technique we use here is an extension of the technique used for the lower bound for small epsilon. In the rest of the talk, I will focus on showing our query lower bound on local list decoding for the small epsilon case, even for low rate codes and even when allowing large list sizes. The main idea in our proof is inspired from a work of Applebaum et al., where they show limitations on non-deterministic reductions that establish hardness amplification. The first step is to reduce to a slightly different decoding problem and then show a lower bound on the query complexity of that problem. Just for clarity, I have kept a schematic diagram of local list decoding on the left pane of the slide. Instead of wanting to decode from arbitrary words in this new problem, we require that first a message is sampled uniformly at random, encoded with the error correcting code, and then XORed with a string of length n, string z of length n, where each bit in z is 1 independently with probability half minus 2 epsilon. We denote this distribution by BSC n half minus epsilon or 2 epsilon. Now, earlier, the requirement was to correctly output each bit of the message with a certain probability. We changed that requirement to a new requirement of having to decode a fraction, a very large fraction of message bits correctly. For those who are familiar, this relaxation is in line with approximate local list decoding. We also observe that given these two requirements, it is enough to consider deterministic decoders. The claim we make here is that local list decoding implies this above decoding task, albeit up to small losses in query complexity. So here is the renewed schematic diagram for this somehow randomized noise approximate local list decoding task. The second ingredient in our proof is that of lower bounds on the sizes of AC0 circuits solving a famous coin problem. So AC0 circuits, for those of who you are unfamiliar, are circuits of AND or NOT gates where the gates can have unbounded fan-in. Now the theorem is that we use is that if such a circuit of depth d can distinguish between BSC distribution with coins of bias half minus epsilon versus BSC distribution with uniformly random coins, then that circuit has to have size roughly 1 over epsilon to the whole d minus 1, whole power d minus 1. Now this result follows from a long sequence of works, and we use this theorem in the following way. Basically, for a given message M, we develop a circuit CM that on input Z outputs 1 if the decoder, the EC, upon oracle access to encoding of M XORed with Z, can decode the bits of the message M correctly and output 0 otherwise. More precisely, so we describe an AC0 circuit that does the following. Our circuit is hardwired with the message M and also the encoding of M. It first computes encoding of M XORed with Z, which it receives as input. Then It checks whether the deterministic Q query decoder, the EC, outputs the correct answer for each of the KL many possible input combinations I and J. These logical conditions are stored in bits Bij. Specifically, Bij is equal to 1 if decoder on access to W and inputs I and J outputs Mi. Now for each value of advice J for the decoder, the circuit computes the conjunction of the bits Bij, and this conjunction indicates whether every bit of M is decoded correctly when this particular J is given as input. The final output is an OR over these bits obtained for different J's. Essentially, the output represents whether there exists a J for which every message bit is decoded correctly. We argue that it is possible to perform these operations using an AC0 circuit of depth 3 and size big O of KL2 to the Q, where Q is the query complexity of the decoder. The key idea is that our decoder is deterministic and can be represented by a Q times 2 to the Q sized circuit. The main issue might appear to some of you to be the hardwiring of the whole of encoding of the message M, which might take n bits, right? But we do not really need to do that. We only need to hardwire those bits of encoding of M that are queried by the decoder on various input combinations. And the number of such bits is not too large. Specifically, it is only KL times Q2 to the Q useful bits. Okay, so we have an efficient circuit checking whether our decoder decodes correctly. By definition of this new decoding task, if the input Z is coming from BSE half minus epsilon, then the decoder succeeds and the circuit CM outputs 1. On the other hand, if the input Z is coming from BSE half, then the encoding of M, the message M XOR Z, will look like is actually a uniformly random string, and CM, the circuit, can decode it correctly only with a really small probability. Finally, by an averaging argument and using the fact that list sizes are still bounded by a small constant times 2 to the k and an amplification of the probabilities, we are able to show that there exists a message M and a corresponding circuit CM that really solves the coin problem. Using this conclusion, and in combination with the lower bound on the size of circuits for the coin problem, we can obtain our lower bound expression by appropriate simplification. We get an expression for the query complexity. So here is the theorem again, whose proof idea we outlined. In particular, we say that local list decoding of codes from half minus epsilon fraction of errors need omega 1 over root epsilon queries when epsilon is small, even if the code has very low rate and even if we allow very large list sizes. Our work leaves several open problems. One immediate open problem is to improve the lower bound for the small epsilon case from 1 over root epsilon to maybe something better. Our lower bound for the large epsilon case can be extended to handle decoding from erasures. Specifically, decoding from 1 minus epsilon fraction of erasures requires a bound of omega 1 over epsilon. We do not immediately see, it is not clear, whether the same can be done for the small epsilon case. So what can we say about the small epsilon case for decoding from erasures? A third very interesting question would be whether non-black box techniques can help obtain better hardcore predicates from hard functions. I would like to bring your attention to the fact that our work rules out only black box techniques and not non-black box techniques. So this is a very interesting open direction. In any case, that is all I have got to say. Thank you for your time. Thank you.